So we spend a lot of time at this point talking about how we can calculate the electric field and the electric potential specifically from point charges, from a single isolated charge that's not really stretched out at any point in space. So to do that, let's say I have some point charge plus Q, it's going to generate a field, so it's the source charge, and I look at some distance r away at this location here. Well, the electric field at that point would just be K times Q over R squared, where the direction of the electric field would be away, because that's the direction a positive test charge would go. And additionally, the electric potential would just be KQ over R, where it would be positive, because this is a positive point charge, so plus Q will give us a plus phi. But the thing is, though, is that realistically, we're not going to see just isolated point charges in our life. A lot of times we're going to have conducting surfaces, and these are going to distribute charges in a myriad of different ways. And we want to know, well, how can I calculate the electric fields and the electric potentials from one of these conducting surfaces? Now, we could literally spend the rest of the year going over some of the details for specific shapes, but we're really just going to focus on one, which is, in all honesty, the most simple, which is a spherical conducting surface. So imagine you have a metal sphere here, and that metal sphere has a radius capital R, so let's keep big R as the radius of the sphere, little r is the distance from the center of the sphere at this point in space. And if we charge this sphere with some charge plus Q, well, those charges are going to distribute over the surface of the sphere, because they're going to repel from each other, they're going to try to get as physically far away from each other as they can, so they're going to occupy only the outside of the sphere. Now, if I want to calculate the electric field or the electric potential from this spherical conductor, well, how can I go about doing that? Because these charges are distributed all over its surface. So if we think about it, if I use the equations I already know, well then I would have to say, okay, from every single charge, what is the electric field from every single charge? And they're going to be different because they're different distances. What is the electric potential from every single charge? And then I would have to combine all the electric fields together, all the electric potentials together, and that would give me the total electric field and the total electric potential at that point. Now, unfortunately, as you might expect, this would be a nightmare to calculate. In fact, it'd be practically impossible. So, how can we go about to simplify this? Well, if we think about it, a sphere is nice and symmetric, and so if we look, it's the same distance to here as it is to down here. So any sort of vertical effects will be canceled out by whatever vertical effects here, so really we can just treat all these charges like they're on the same horizontal line. And additionally, some of the charges are closer to point R, this point right here. Some of the charges are further away, but they also balance out. And so ultimately what this is telling me is that due to symmetry, and this is a real, lucky thing for us, that due to symmetry we can just pretend that this entire charge is really just at the center of the sphere. Because at any point outside of the sphere, it's not going to behave any differently. So if you were sitting at this point here, if you were this distance r away from a point charge with plus Q, or away from a spherical conductor with charge plus Q, they would behave exactly the same way. And so because of that, we're going to essentially say, well, I've got the spherical conductor, let's pretend all of the charge is at the center, and then go from there. So when we are looking at points outside of the sphere, or on, so when r is greater than or equal to big R, when this distance is outside of the sphere or on the surface of the sphere, we can calculate the electric field and the electric potential as though all of the charges that were on that sphere were just at the center. And to do that, well, we just use the equations we already talked about earlier. E is KQ over R squared, V is KQ over R, the electric field will go to the right because that's the way positive test charge goes, and the electric potential will be positive because of the fact this is a positive charge. Nice and simple. However, that was only talking about places outside of the sphere. Well, that's not all of space. There's also literally locations in the sphere. So how can we figure out the electric field and the electric potential if r, little r, is less than the radius big R, if it's at some point inside of this spherical conductor? So remember, the spherical conductor has a positive charge all around it. It's this positive Q. They're all distributed over. So how could we figure that out? Well, we've actually already talked about the electric field. Because this is a conductor, remember we learned this in class, well, that is basically an example of electrostatic shielding. That all these charges on the surface, basically all of their effects cancel out inside the sphere, and we're actually going to have an electric field of 0 inside the conductor. So if we put a charge there, it would not experience any force at all. Now going a step beyond that, well, okay, if I know that the electric field is 0, well, remember I have this equation that E is equal to the change in potential, so the voltage, over some change in R, some distance. Well, if E is 0, the electric field is 0 inside the sphere, well, what does that tell me? It tells me that the change in potential must be 0, too. And if the change in potential is 0, that means the potential must be constant at every point inside the sphere. So, because that is the case, in fact, it will just be equal to what it is at the surface. So at the surface of the sphere, V would equal to kq over big R, where R is the radius of the sphere, and all of the potentials inside will just be exactly the same. They are all going to match that value. Okay, so kind of to help us think about this, let's say we have two graphs here. This is showing me the electric field in newtons per coulomb with respect to distance from the center of the sphere, and this is the electric potential in volts or joules per coulomb at some distance from the center of the sphere. The sphere has some positive charge plus Q, and let's say, so R is the radius of the sphere. So this part here, that would be inside the sphere, and this will be outside the sphere. So first off, let's look inside. So inside, the electric field is 0. It just cancels out at all points inside the sphere, and the electric potential will be a constant and specifically be equal to kq over r, where r is the surface, the distance to the surface. And if we look outside the sphere, this region outside, the electric field immediately jumps up to kq over r squared, and then it's going to go down as 1 over r squared for the distance, just like any other inverse squared graph. And V will go down kq over r from this point. So it's going to be the same right here, but then it's going to decrease at like an inverse curve. Let's just do a brief practice problem to make sure we understand this. Let's say we have some sphere. It has radius 0.5 meters, and the charge on it is -4 microcoulombs, and those negatives are going to redistribute over the entire surface of this conducting sphere. And we want to determine the electric field and electric potential at 2 points. A, which is 0.3 meters from the center, which is going to be inside the sphere, and B, which is 1.5 meters from the center, which is outside the sphere. Well, let's go ahead and look at A first. Well, the electric field is going to automatically, we know, be 0, because it is inside the sphere, and there are no charges inside the sphere. All the charges have been moved to the outside, and the electric potential will be kq over r, so that'll be 9 times 10 to the 9th times -4 times 10 to the -6. Now, careful, and I even made a mistake here. This should not be 0.3. This electric potential is what it is at the surface, because it's constant through this whole region, and it's equal to what it is at the surface. This should be 0.5 meters, but I believe, double checking my numbers, that this does come out to be the right value of -720,000 volts. Now let's look at point B. Well, for point B, we are outside the sphere, so we just treat it as though all of the charge was located at this point right here. And so I'm just going to say, all right, well then kq, we're going to have it all go to that center point over r, where r is 1.5 meters, and that'll be 16,000 newtons per coulomb toward the sphere, because a positive test charge would be attracted to it. And the potential will be kq over r, where I just stick those in, and I get -24,000 volts. That's all there is to it.